Okay, welcome to another live session. It's been a little while, for which I apologize. I was traveling. I was in Italy for a month, no hardship there, teaching at the Vatican Observatory Summer School. That's a topic to talk about at some other time. It's a very exciting opportunity for young graduate students from around the world to study a topic in astrophysics in detail for 4 weeks in the heart of Rome, or basically in the heart of Italian culture. And the topic for the school this time was water in the solar system and beyond. So I was lecturing on that, and I got to meet my third pope, actually. Not that I'm counting or boasting. Well, okay, a little bit. So the floor is open for your questions.
All right, the first question is from email, and it is a comet really made of icy water? What percentage of it? And could we catch a comet anytime in the future?
Right. So the composition of comets, the story hasn't changed dramatically. One of the pioneers of cometary studies was a man called Fred Whipple, who did most of his work in 50 or 60 years ago, actually. And he came up with what became known as the dirty snowball theory of comets. So originally, it was always understood that comets had icy material in them because even if they're mostly rocky material, it's the icy material getting blasted off by the sun's radiation that makes the comet tail and also the coma of a comet. But the relative proportions of these materials was not really well understood. Whipple came up with the idea that they're dirty snowballs, so essentially saying that a good part of the material, perhaps the majority of the material, was icy material. Now, astronomers use the term volatiles for the icy material in the solar system, by which they mean a set of ingredients or molecules which are typically found in the ice phase out in the solar system, which is where comets spend most of their time at very low temperatures, and which can either melt or boil off when they come close to the sun, as comets do, but not all comets do. And volatiles, of course, can include liquid water in its frozen liquid and gaseous form, but can also typically include carbon dioxide, because that's a very abundant gas in the universe, which would be, of course, dry ice and no liquid phase going straight to a gas. That can also include ammonia, another common ingredient in the solar system, which could be in a frozen liquid or gaseous form, and a set of other ingredients. So after Whipple's model, the paradigm became equal or maybe more proportion of the cometary mass in volatile material. And that was accentuated by the first few cometary rendezvous. We've now rendezvoused with a handful of comets and sampled the material. And it really does seem like they're very loosely held together rocks with mostly icy material at the junctures between the rocky material, almost like a rubble pile held together by ice. But not every comet is the same, and some comets have been rockier than others and had more substantial continuous areas of rock. But the general view is indeed that most comets have most of their material, the majority by mass, in the form of volatile frozen gases rather than rocks. Now, of course, a comet will evolve over its time because they're on periodic orbits, and especially those that where their orbits bring them into proximity with the sun or into the inner solar system, they will lose some of their volatile mass by it being boiled off by the sun each time. And so we can imagine that over a period of hundreds of thousands or millions of years, comets will actually dry out. And some of them, if the icy material is sort of holding the rocks together, will come apart, will disintegrate, essentially. And there's evidence that both of those things happen.
All right, the next question is again from email, and they would basically like an overview of the gravitational wave discovery and what it means for the future of science.
So the overview is important because this is a rapidly changing field, and also I can use the opportunity to note that in the last month there was a second gravity wave discovery. The actual detection took place a few months ago, but of course they're very cautious, so they take a while to publish and announce it. So there are two solid confirmed gravity wave events from LIGO, and there's actually a third possible event that took place late last year. And that's simply just too weak in terms of signal for them to be confident of it. So they're not calling it a detection. But we have two detections from that first LIGO science run. So the short story is that a new field of science has been born, gravity wave astronomy. It's real, with multiple detections. We know that the first one wasn't a fluke, that there are coalescing and colliding black holes out there in the universe. And the other pattern, in as much as you can draw a pattern from two detections, is also striking because the distances of the first two LIGO events were 1.1 and 1.4 billion light years. So these gravity waves did not come from binary black holes colliding and coalescing in the Milky Way galaxy, our galaxy, nor even in the nearby universe, but actually from the distant universe, from galaxies very far away and very far back in time. And that's interesting in its own right. That implies that the scope or the reach of the LIGO instrument is extraordinary, because if the first two events came from as much as 1.5 billion light years away, that means LIGO is sensitive to events like that in the inner 10%, in 10% of the space-time available in the whole universe. That's an extraordinary volume, including millions of galaxies, all filled with black holes that could potentially collide. So it's very exciting because it essentially guarantees that LIGO will continue to detect things. The other surprise from the first two LIGO detections is the mass of the black holes. The second event, the more recent one, represents the coalescence of an 8 solar mass and a 12 solar mass black hole to form a black hole that is actually 1 solar mass less than the sum of the two. The math is not A plus B equals C. It's A plus B equals C minus 1 solar mass, because that 1 solar mass was actually converted into gravity wave energy. So we have mass energy conversion into gravity waves. In the first binary detection, 3 solar masses of stuff were turned into gravity wave energy and radiated out into space. The first event is still considered extraordinary. A reanalysis of the LIGO event, the first one, and a republication just in the last month or so, has upped the mass of the two black holes. They were originally both considered to be less than 30 solar masses, which is high, but now they're thought to be 30 and 35 times the mass of the sun. And that is extraordinary, because that is essentially much higher than we had any expectation of black holes in the nearby universe. Because something that dies and leaves behind a 30 or 35 solar mass black hole has had to live its life and lose a lot of mass to get there. So it probably started as an 80 to 100 solar mass star each. And that's at the very high end of what we think stars can be in terms of mass. So it's pretty unusual, and it's been making people scratch their heads how the first binary black hole event could involve such massive black holes, pretty much at the limit we expect stellar black holes to be. And that's still not understood. And that's why we need more events. So to summarize, LIGO works beautifully. With 2 and confirmed and 1 possible event in the first 5 or 6 months of operation, and there are probably more events that can be teased out of the data with enough time. We're going to expect a LIGO event roughly every month, so a dozen a year. And so within a couple of years, this new science will have a statistical basis for talking about the incidence of black holes in the larger universe, the properties of those black holes, deep levels of confirmation of general relativity in terms of the signatures of those black holes as they coalesce and release gravity waves. And so, a very exciting result. And of course, the other part of the story is that the success of LIGO, after some skepticism and even among physicists that it might not work, that it was overly ambitious, it has kickstarted the idea of other gravity wave detectors. So the Europeans, who already had a gravity wave machine planned, have accelerated their work. The Japanese have one that's being constructed. There's going to be one in India. So there should be 5 or 6 gravity wave detectors instead of the 2 that LIGO has within a few years. And also, it's reanimated the idea of a space-based interferometer that can detect huge black holes coalescing. That's the LISA, L-I-S-A project. That's got some funding from the European Union recently for a design study. So gravity waves are hot, and they continue to be hot and will be for the next few years.
All right, the next question is about stars. How is absolute brightness or magnitude of a star determined versus apparent magnitude?
Right, so astronomers are intensely annoying because they, claim, pretend, and are legitimate scientists, but they, in some areas, adhere to archaic units. Now, the excuse astronomers have for their archaic units is that astronomy is the oldest science and it started as a naked eye subject. And so astronomers have long used what's called the magnitude system. And the magnitude system, in terms of the written record of it, started with Hipparchus. So that's almost 2,000 years ago. Hipparchus produced the first star catalog. And in that catalog, he had to define the brightness of the stars in the catalog. And there was no detectors, no digital or numerical measurement of brightness. You were using your eye. The eye is a logarithmic detector, which means it has a nonlinear response. And so Hipparchus essentially divided the stars into the night sky into 6 rough groupings of brightness, from the very faintest things you could see at the limit of your vision from a dark place to the handful of brightest stars in the sky like Sirius and Arcturus. And those divisions became magnitudes. And it turns out that there's a factor of about 100 between the brightest star in the sky and the faintest star in the sky. So 5 magnitudes, the divisions of the original magnitude system, correspond to a factor of 100. So in a logarithmic scale, that essentially defines what a magnitude is. Now, those are apparent magnitudes. And because astronomers have to be even slightly more annoying than just using nonlinear logarithmic units, they also used reverse units, where 0 magnitude, corresponding roughly to the brightest star you can see, is brighter than 6th magnitude, which corresponds to the limit that you can see with your naked eye. So in this system of magnitudes, the higher number corresponds to the fainter object. Okay, so that's all apparent magnitude. If you have an apparent magnitude, just as how bright the star appears to be, which is just how many photons per second are coming to your eye or a telescope or to the Earth's surface. What you really care about, of course, is how intrinsically bright a star is, because two stars that appear of equal brightness in the sky to your eye may be at very different distances, and therefore the one that's much further away is much more luminous, intrinsically more luminous, and is actually emitting more photons per second, but fewer of them reach the Earth because it's further away. It's diluted by the inverse square law of light propagating in the universe. So absolute magnitude uses the distance, combines it in a logarithmic scale with the apparent magnitude, how bright it appears, and produces the absolute magnitude, which is the true brightness of an object in terms of photons per second, but still in this logarithmic scale. So that's a long explanation for a rather cumbersome system. The truth is that in most areas of astrophysics and stellar astronomy, magnitudes are still used. They're used in catalogs, and amateur astronomers, of course, still use them. But for doing calculations about luminosity and mass and temperature and stellar properties, people use linear units. They use SI units and metric units.
All right, the next question is about energy. And the question is, why do we define energy the way we do? And more specifically, why do we define a unit of energy as 1/2 mv squared? Why not redefine the unit of measure and eliminate the 1/2 and simplify the equation?
Okay, so the way we define energy, that's an important question in physics. So the example in the question is just one form of energy. It's kinetic energy, which in physics is half the mass times the velocity squared. The nature of that equation and why there's a half in it essentially comes from, in a sense, from the system of units, if you're working in metric units. And so you're going to have mass in kilograms, you're going to have velocity in meters per second, and then that's going to define what your energy unit is, and that leads to the half. It's just a mathematical derivation. But remember that kinetic energy is only one form of energy. The most generic physics type definition of energy, which has a sort of Zen-like quality to it, is physics is the ability to do work. That sounds rather strange because it just refers energy to something else, work. What does that mean? That's moving something, liberating energy in another form, having the energy cause a change in a system. So energy is a nimble agent in physics for things happening, for changes occurring. Kinetic energy, which is the energy of bulk motion of an object involving its mass and its velocity, is just one form of energy. There's also potential energy. So that same object could be moving and have kinetic energy, but also be sitting in a gravitational field, such as on the Earth's surface or traveling above the Earth's surface. And that means it has gravitational potential energy, which is related to its mass, its height above the center of gravity of the Earth, and the gravitational constant. And so that's how the potential energy of gravity of that same object is defined. That same object can also have an equivalent mass energy, and that's defined by Einstein's equation, E equals mc squared. So then you take the mass in kilograms and multiply it by the speed of light squared, obviously a very large number. So the amount of energy implied by the mass of an object is huge, and it's phenomenally larger than either the kinetic or gravitational potential energy of a normal object in a terrestrial environment. So there are a number of forms of energy, and physicists just try to be consistent in their use of units. And if you're using consistent metric units or System International units, SI units, then the equations have to come out a particular way.
Right. The next question is, what will it take for cosmologists to be able to see back to the dark ages of the universe? Is our accelerating expansion going to make that impossible?
They're very close. Cosmologists are very close to the dark ages. The highest redshift, so remember redshift in cosmology is the amount by which radiation is shifted to longer wavelengths by the expanding universe as the light travels through the universe. And it's in the Big Bang cosmology, that's related to distance. So there's a conversion between redshift and distance. The highest redshift that are believed, there are claims of high redshifts pretty much every few months, but some of them are controversial. So the highest redshift that are believed at the moment are redshifts of about 10. And that represents an order of magnitude shifting of the light and loss of energy since that light was emitted. And if you use the cosmological model to convert a redshift of 10 into a look-back time, it corresponds to a little over 13 billion years, roughly 13.2 or 13.3 billion years. So in a universe that's 13.8 billion years old, that's less than half a billion years after the Big Bang. And that is believed to be very close to the dark ages. So a redshift of 10 or 11, which is the highest plausible claim for a high redshift galaxy, is among the youngest galaxies you could imagine existing in the universe. They can't have been in existence very long. We believe the instrument that'll get us there is James Webb Space Telescope, but Hubble might actually do it the first in the next year or so. Hubble's working flat out. It's not a big telescope, but has good infrared detectors. So people are still trying to find the oldest light in the universe. James Webb was built for that project, so it'll do it for sure. So I would say we're extremely close to the dark ages already. As for the last part of the question of what impact the accelerating expansion will have on this whole initiative or on cosmology in general, well, it's not good news in the long term, because it will take objects that we can currently see, whose light can currently reach us, and stop them from ever being visible again. Because remember, the universe did go through a decelerating phase when dark matter was dominant before dark energy became dominant 5 billion years ago. But now, from the last 5 billion years and on into the infinite future, dark energy will pull all parts of the universe faster and faster away from each other, and that will wrench from our view objects that once were visible to telescopes. And so in some long-term sense, and by long-term I do mean 1 billion or 2 years in the future, all the galaxies we can comfortably measure now will be removed from our view, not just the very distant ones, but actually the fairly nearby ones too.
All right, the next question is from Gerald, who's on with us live. We know that the mantles of Jupiter and Saturn exist as, I guess I'm assuming he means atmosphere. We know that the atmospheres of Jupiter and Saturn exist as molecular hydrogen. Does that mean that it's some kind of diatomic molecule? Is it deuterium? Like, what do we know about them?
So the cool atmospheres, so I think the question relates to the cooler outer parts of the atmospheres of the gas giants. So in the stratified atmospheres of Jupiter and Saturn, particularly the gas giants, there's an enormous temperature and pressure gradation through the atmospheres. down where we believe there is actually a rocky core in Jupiter and Saturn, also Uranus and Neptune too, we think the atmosphere, the hydrogen and helium atmosphere of the gas giant is actually compressed into a form of metallic hydrogen mixed with a little helium. It's an extraordinary situation. Densities hundreds or thousands of times higher than terrestrial situation. And so that's also a very hot place, hot and dense. So if you move up through the atmosphere, you actually do get to a place where, you know, in normal terrestrial terms, it's about room temperature. And Carl Sagan and Ed Salpeter in 1972, I think, possibly 65, not sure of that date, wrote an interesting paper speculating about buoyant jellyfish-like life forms in the atmosphere of Jupiter, just living on the circulation patterns of the atmosphere at a sort of room temperature, a plausible temperature for life. That was an extraordinary speculation. So as you move further out, the atmosphere becomes cold. Eventually, of course, it becomes very cold because at the edge of the atmosphere, you're in deep space, far from the sun, so the temperatures are hundreds of degrees below 0 centigrade. But there is a zone somewhere near the sort of quasi-habitable zone of Jupiter and Saturn where it's cool enough for molecular forms to exist and diatoms and so on, as the question implies. And there you can have molecular hydrogen, you can have methane, ammonia. There are various slightly more complex molecules that exist in trace amounts. And that's that kind of rich chemistry that exists in these cooler outer regions of the atmosphere. It's also responsible for a lot of the coloration of Jupiter. When we look down through the atmosphere of Jupiter, a lot of the coloration and the banding patterns, and especially the darker, apparently darker regions, are caused by some of these molecules like ammonium. And hydrogen sulfide is another one, sort of all essentially the 2 and 3 atom molecules you can imagine given the basic ingredients. So the molecular structure or composition of the Jovian planets is very interesting, actually, and it's not still fully understood. Now, Juno, of course, is going to take its death dive into the Jovian atmosphere and will actually sample directly the Jovian atmosphere in its last few hours.
All right, the next question is about some fairly fundamental physics. Can you please talk about the Planck units of mass, length, and time, and their importance in general and for a unifying theory of everything?
So in the sort of cutting edge of physics where people try and unify the 4 forces of nature, there's a fundamental scale at which our current theories break down, and that's the scale. And I use scale in a general term because it relates to all the physical properties. There's a scale at which we can unify relativity, general relativity, our theory of gravity, and the quantum theory that describes microscopic physics. Now, if you go through the math of making the coupling between essentially the gravitational constant, which is the constant of nature that relates to gravity, and the Planck constant, which is the constant, a very small number. They're both very small numbers, but one much smaller than the other, that relates to the quantum scale, then you come up with this characteristic Planck scale. And so that's what the questioner is relating to. So the Planck scale essentially is referring to scales of physical quantities where gravity and quantum phenomena have to be considered equally important together and have to somehow to be unified in a theory. We don't have such a theory, so it's a very speculative thing. The Planck scale is a scale we can't access through experiment. It's a scale where we don't really understand how the physics works because we're waiting for some string theory or some quantum gravity theory that we don't yet have to test. But what it does represent is a scale of energy, a scale of time, a scale of mass, all the fundamental units, and a scale of size. The size scale, the time scale of the Planck era in terms of the history of the universe is 10 to the minus 43 seconds. So a fantastically small jot of time after the Big Bang. The energy scale of the Planck constant or the Planck unit is about 10 to the 27 Kelvin. 1 with 27 zeros Kelvin. Again, an unimaginable energy. The physical Planck scale is also an incredibly small number. It's of course the strength, the scale of strings in a string theory. And so we have scales Planck scale numbers that we can talk about and we can calculate, but we have no physical theory that properly describes what happens at these scales.
All right, the next question is also from a live viewer, and it is Jupiter and Saturn are hydrogen and helium, but their moons are made of rock and or water. Why is the composition of the moons so different than the parent planets? Both are formed from the same matrix at about the same time. Do we know?
Yeah, it's a miniature version of what happened in the solar system itself. That the analogies between giant planets and their moons and rings and the solar system itself as a whole are quite good analogies. And that's because a lot of the physics is what's called multiscale, like turbulence. Turbulent theory is involved in how gas clouds collapse to form planets and stars. And turbulence is a multi-scale phenomenon where you can have eddies and condensations on one scale that look very similar to condensations and eddies on a much larger scale. So you have a multi-scale phenomenon, which means that you can physically correctly make analogies between the solar system as a whole and a moon forming around a planet. So conservation of angular momentum is important. So as in the solar system as a whole, when a giant planet forms, it forms from a large region of gas that has a general amount of rotation, and the collapse is preferential along the polar axis of that rotation, so you tend to form a disk. And the disk of gas and dust is what leads you in the end to form a planet and its moons and its rings all in one plane. Now, it's not true that all the mass of rocky material ends up in the moons, because we are fairly certain, and Juno is going to nail this for Jupiter at least, that all the gas giants have rocky cores. The mass of those rocky cores is very uncertain, but the mass of the rocky core in Jupiter, depending on the measurement and the argument, is somewhere between 5 and 10 Earth masses. So that's more than a super Earth. That's quite a substantial rocky mass. So if you think about that, then the stuff that formed Jupiter did have rocky material, and that rocky material went into a core that then accreted hydrogen and helium as an envelope. And if that rocky core is even 5 times the mass of the Earth, that amount of mass of rocky material is far more than the sum of all the moons of Jupiter, because the Earth is a substantial sized planet, and even Jupiter's biggest moon is about the size of the Earth moon. So still, even though there's not much rocky material in the planet, there's more than in the sum of all the moons and the rings. What happens then is that the gas essentially dissipates. So in the central part, you have a rocky core. That's just the proportional amount of rocks relative to hydrogen and helium, where it's still vast majority, 99-point-something% hydrogen and helium. So the rocky core is a small percentage. And then further out, you have a situation where the rocky material gradually aggregates together to form moons, or not. The rings could be failed moons, for example, and some of those rings are actually moons that just got destroyed while they were being pulled together by gravity, and so ended up as rings. And then the gaseous material, the hydrogen and helium left over, just sort of dissipates over time or gets driven out of the system by being heated up by collisions with the particles. So you end up with a sort of distillation process, to use that term loosely, where beyond the giant planet, you're left mostly with the rocky and dusty material, and you don't see a lot of the gas because it's either driven away, drifts away, or dissipates. Whereas the rest of the gas near the center of the system is held together by gravity to form the giant planet itself.
The next question is related to something you were just talking about. Can you explain what Juno will be telling us about Jupiter during its mission?
Well, Juno is trying to understand. Juno is a high degree of difficulty mission in the NASA portfolio, because it's venturing into an area where you need a totally battle-hardened set of instruments to handle the enormous stresses of the magnetic field and the cosmic rays and the high impact rates potentially in that space environment. So Juno is looking at the Jovian system with a view to understanding the source and the nature of the magnetic field, with the view to understanding the size of the rocky core that we have believed for decades sits in the middle of Jupiter, but we've never measured its mass very carefully. And of course, giving us some very detailed insight into the way the atmospheric patterns and bands and clouds on Jupiter work. Even though Jupiter has been observed in the telescopic era for over 400 years, we still don't have complete understanding of the energy flow within the atmosphere, the cause of the banding structures we see, the differential flows of gas, the formation and persistence of large features like the Great Red Spot for centuries, how they evolve, why they dissipate, why they persist. So Juno is going to give some very detailed information on all of these things, and it has a range of instruments. It's a pretty sophisticated instrument. And since giant planets are abundant in the universe, we now know this through the discovery of many exoplanets, many of which are Jupiter-sized, it's going to paint the picture of our archetypal giant planet in our solar system that we think will apply to all these exoplanets that are being discovered.
All right, the next question is about orbital dynamics, and it is, can you please explain the efficiency of carrying out orbital transition maneuvers in the lowest point of the orbit, but the inclination change at the farthest point? I'm assuming this means for spacecraft traveling.
Yeah, you're going to have to repeat the question. I got distracted.
Why is it that spacecraft carry out orbital transition maneuvers at the lowest point of the orbit, but inclination changes at the farthest point of their orbit?
It's a sort of a question of energy. So at your lowest point in your orbit, I mean, if you're following Keplerian mechanics, which spacecraft are, they're in elliptical orbits, then at your lowest point in your orbit, you have the highest velocity, so the highest kinetic energy, and the lowest gravitational potential energy, and that's the converse at the other extreme. So to change inclination, you actually want your kinetic energy to be at the lowest, so your velocity of your spacecraft to be lowest, because that requires less thrust from your little rockets to change your inclination. So it's just easier in energy terms because of Keplerian orbital dynamics to change inclination when you're at the extreme of an orbit, moving the slowest.
So the next question is from somebody who is on with us live, and they ask, why is it that cosmic microwave background radiation is called the oldest light in the universe?
It's because well, of course it isn't light. As measured, it's microwaves, but as emitted, it was light. So there's a little artistic license in calling it the oldest light. However, it is correct to say more generally that it's the oldest radiation signal in the universe, because the microwaves were released or emitted or traveled to us starting from a time when the universe first became neutral, which is to say, before that time, 400,000 years after the Big Bang, the temperature was hot enough that hydrogen atoms and helium atoms, which is what most of the universe was, didn't exist. All we were talking about was helium and hydrogen nuclei, or protons, and free electrons. And light could not travel freely in that situation. In that kind of a plasma, the electron scattering of photons off of electrons actually makes the situation opaque, so light cannot travel freely. So radiation of any kind cannot travel through the universe freely to give us a view of it, to make an image, to see a contour, a surface, until matter becomes neutral. And that's what happened after 400,000 years, after the Big Bang. And at that time, that's a redshift of 1,000, just a little more than 1,000 compared to now. And since redshift is the amount of stretching, the microwaves we see that have centimeter-type wavelengths now, 13.7 billion years later, back then had energies or wavelengths that are 1,000 times shorter. And that actually makes them, at a temperature of about 3,000 Kelvin, sort of dull red photons. So at the time that radiation was first released, it was indeed the first light in the universe, and it was a dull red kind of light from photons that had a wavelength corresponding to a temperature of 3,000 Kelvin. In the intervening time, traveling through space, where space-time is being stretched by the cosmic expansion, all those photons have been stretched from dull red photons to be microwave photons, and that's how we detect them now on the Earth.
All right, the next question is it possible that two galaxies move away from each other faster than light?
Yes, absolutely. So it's part of the standard Big Bang model that at some points in the previous history of the universe, in fact, about the first third of the history of the universe. So if the universe is 13.8 billion years old, that means for the first 3 or 4, maybe 5 billion years, any 2 points in space that you might pick, they don't have to have anything sitting there, just points in space, were moving away from each other faster than the speed of light, because the universe has been decelerating, or was decelerating in the first 2/3 of its history. And if you just trace the expansion rate back, that's a very clear prediction of the Big Bang model, that will be before a certain amount of time ago, all points in space were moving faster than light away from each other. And if those points in space happen to be positions of 2 galaxies, then those galaxies were moving away from each other faster than light speed. So it's a completely standard part of the expanding universe picture. But remember that the universe was decelerating, and so many of those galaxies do come into what we would call causal contact, where signals or light can travel between them subsequently. So having been superluminally expanding, the universe slowed down, and that means things that could not communicate with each other through light signals may subsequently be able to do so.
Right. Our next question is, how does adaptive optics clarify the images that we get from telescopes?
It essentially compensates for the turbulent motions in the Earth's atmosphere that lead stars to twinkle and that blur out the images from even the best astronomical sight to something like 1/3 of an arc second. So if you go to the best, if you're in a standard urban location or outside the city at sea level, a typical seeing or blurring of the atmosphere caused by the atmosphere of incoming starlight is 1 or 2 seconds of arc, 1 or 2 arc seconds. That up on a high mountaintop observatory in Mauna Kea or Chile is going to be a lot better, 4 or 5 times better. So of those best observatories, the seeing is about 1/3, maybe the very best 1/4, but about 1/3 to 1/2 an arc second. But that's still a lot of blurring compared to the resolution defined by the optics of your telescope, which would be the diffraction limit of that telescope. That resolution for a few meter-sized telescope should be 1/100th of an arc second or less. So you're losing a lot of resolution compared to what you would say in space. The Hubble Space Telescope doesn't have to deal with this blurring, and its images are extremely sharp. So adaptive optics is a method to essentially cheat the atmosphere, or almost completely compensate for these turbulent motions. So, and what is causing the blurring? So the upper atmosphere convective patterns of turbulence is also associated with variations in density. And since light will travel at very slightly different speeds through media of different densities, including air, those density variations in the convective region also cause light to be refracted slightly as it travels through these different density zones, both transverse and longitudinally as it comes towards the Earth's surface. And the effect of all that is to just alter the straight linear path of these light rays and sort of jumble up the light, and also make it change from second to second, because these turbulent motions are continuously changing, and that's what makes a star twinkle, visible even to the eye and through a telescope as well. So to compensate for this, adaptive optics has to measure what the atmosphere is doing to the light so that it can compensate for it. And the way that's currently done is by shining a high-powered laser, typically a 100-watt sodium laser. That's a pretty powerful laser, the kind of thing you don't mess with. It could blind you or cause some real damage. That's a powerful laser. You shine that laser and bounce it off the same upper atmosphere layer that's causing the jumbling of the starlight. You collect the light, the reflected light, that laser light that you've just sent to the same atmosphere that's causing the problem. You collect it with a small telescope attached to your large telescope and measure how the waves of light are being distorted by the changing atmosphere. Then you feed that information into your main telescope and adjust the secondary mirror of that telescope. You do this as a secondary because it's a smaller mirror. For a huge telescope, that might be a 1 meter mirror rather than an 8 meter mirror for the primary. And then that mirror is designed to be thin, maybe 1 millimeter thick, 1 meter across, and with actuators, maybe hundreds of actuators with little piezoelectric adjusters on them. You compensate the shape of that mirror to perfectly take out the variations in that layer of atmosphere that you diagnosed using a laser. So that's kind of a long explanation for something that is actually quite complicated to do, but now is routine at all the world's largest telescopes.
Right, the next question is from someone via email. What is the Higgs boson, and is there any connection between the Higgs boson and gravitational waves?
So the Higgs boson or particle is the boson part is a high energy physics term, just meaning that it obeys Bose-Einstein statistics, has integer spin in terms of its quantum properties. The Higgs particle was predicted and obviously led to a Nobel Prize to Peter Higgs from the University of Edinburgh, my alma mater, where I got my PhD just a few years ago. So the Higgs particle or Higgs boson is a predicted part of particle physics that essentially causes particles to have mass. So one of the mysteries in particle physics, the standard model of particle physics as it's called, is why do the particles have all the masses they do? Why are protons and neutrons about 2,000 times more massive than electrons? Why are there intermediate mass particles or mesons that are like the muon is 270 times more massive than the electron? What causes these mass ratios? And then there are evanescent particles with short decay lives that are even more massive than protons and neutrons. All of these particles, quarks, electrons, muons, mesons, etc., have very particular properties, and the theory doesn't really say why. It doesn't say why they have the masses they do. So the Higgs mechanism, and it's really a mechanism rather than a particle, is the hypothetical tool to explain how particles get mass. And really what it is, in physics terms, is a field. So we think of a field as being like the electromagnetic field, which can permeate space, or the gravitational field, which also permeates space, because these both obey 1/r² laws, and so they never actually go to zero. So there's always electromagnetic field in space. There's always gravitational field in space. And the Higgs field is just another kind of field in terms of physics, which is the motivator for mass. It's essentially the trigger or the cause of mass. So we can think of it, if we have to analogize it, we'd analogize the field that pervades space, this Higgs field, as something viscous, or something that causes resistance or impedance to objects moving through it. And the way different particles interact with the field just gives them different amounts of inertia, affects the way they move, the way they change direction, and so gives them the appearance, because of the way they're interacting with this field, of higher or lower mass. So it's a sort of sleight of hand where mass for a particle is not simply an innate property of a particle, end of story, but mass is ascribed to a particle by its quantum properties, which dictate how it relates and interacts with this field that pervades space, the Higgs field. So it's a little more subtle than just calling it a particle. It is not really a particle as such, it's a field. And the discovery of a resonance at a particular frequency in the Large Hadron Collider affirmed really the simplest theory for the Higgs field that had been around since the 1960s, and it was a stunning success for a prediction that had been out there for decades that had never been tested. So we do think we know where mass fundamentally comes from because of the Higgs detection.
Right, the next question, and we have about 10 minutes remaining, is how does interferometry work to make it seem that our array is a single telescope with the size of the array?
So interferometry was a trick, if you like, developed first by radio astronomers in the 1950s, actually. So it's been around for over half a century to make your telescope seem bigger than it is. And most of the gain of an interferometer involves angular resolution rather than collecting area. So, for example, if you take the elements of the VLA, the Very Large Array in New Mexico, which has 27 antennae, 15-meter antennae spread over tens of kilometers in the San Agustin Plain, the gain in collecting area of those dishes relative to one of them is just the number of dishes. It's 27 times more radio collecting area. But the gain in angular resolution, by having those dishes separated over, say, 15 kilometers, where each dish is 15 meters across, is a factor of 1,000. So you can see that the angular resolution gain in principle is enormous, because you've essentially said, well, we have a telescope with the angular resolution of the largest separation between the elements of the interferometer. So the requirement, that's the principle, that's the sort of general idea. You're taking separate dishes or antennae or array of elements of an array in radio wavelengths. You're creating a separation between them, and you're combining the signal to make it seem like you have one large telescope with the separation between those two elements, and that's its diameter. And it has the angular resolution appropriate to that diameter, because angular resolution scales directly with diameter. Larger diameters, better angular resolution. So this was done by radio astronomers starting in the 1950s, and the requirement on it, the technical requirement, is you have to be able to combine the signals coherently between the different antennae. Let's just imagine it's two, but it could be as many as you want. And what that means is you have to take the signals from the back end of each telescope and preserve the phase information of the radiation, so that you combine them, you don't lose the phase information. Because what you're really doing in an interferometer is forming fringes, just like in a young slit experiment in physics. And you can't make a young slit experiment unless you preserve the phase information of the radiation. So radio astronomers do that for the longer waves of radio astronomy, which are typically centimeters in length. They can do that in several ways. They can do it with waveguides or coaxial cables, or actually with microwave beams between the telescopes. So radio astronomers developed ways of combining this information from different dishes, preserving the phase information, forming fringes, and then using the multiple signals to eventually reconstruct a map of the sky with much higher angular resolution. Now, after the 1950s, sort of into the 1960s, they developed the way of doing this even more ambitiously. So this method called VLBI, very long baseline interferometry, was developed in the mid-1960s to late 60s. And that's where they actually were able to combine signals from radio telescopes, not just separated by a few hundred meters or a kilometer in the same site, but by combining radio telescopes on different continents, and actually even including an orbiting radio telescope. That was done also 30 or 40 years ago. Now, to do that, you actually have to be a little clever, because there's no way you can't have coaxial cable or a waveguide connecting telescopes that are separated by an ocean. So that method could not mature until there were accurate atomic clocks and actually sort of high bandwidth tape recorders, if you can think of old style magnetic tape recorders. So those technologies had to mature, and then basically each radio telescope would record its own signal, the very accurate timestamp from an atomic clock. Then those tapes, literally the magnetic tapes, they'd just be sent around the world, mailed around the world back in 1968 or 69. And then they would using a computer, combine those radio signals after the fact and recreate the fringes and then create the radio maps. And that technique too, as ambitious as it sounds, has been mature for 30 or 40 years. So we've been making radio images of the sky with angular resolutions of about 1/10 of a milliarc second, 10 to the -4 arc seconds, far, far beyond what any optical telescope can do by this interferometry technique extended to Earth-size scales.
Okay, the last question is from Stephen, who sent it via email, and it's, what part of Kitt Peak Observatory and local area is a must-see for visiting? Where is a favorite view or location for unaided stargazing in our area?
Well, Kitt Peak has visitor nights and viewing nights, and that's a good place. Kitt Peak is not as dark as the darkest sites in southern Arizona. The Arizona telescopes that are darkest are at Mount Graham, but it's actually hard to visit that as a non astronomer, non-technical person. So Kitt Peak is always the first recommendation. But if you have a small telescope or even good binoculars, or know someone who does, there are places you don't have to go high up or far out. Beyond Gates Pass, there are park areas which are really pretty dark, because you're kind of shielded by the Tucson mountains from Tucson city light. And that's not too far to go. It's not as long or far or high as Kitt Peak. So that's a second possibility. There are other observatories where you can make a prior arrangement and get to see them. So Mount Lemmon Sky Center is at 10,000 feet, so that's also fairly near Tucson, so it does deal with some city light, but they have what is the largest telescope available, 2-meter telescope available for public viewing. You make online reservations to the Mount Lemmon Sky Center, and that's a pretty big telescope for sort of stargazing and amateur astronomy. And that's available, a lot of the nights of the year, so that's another place to go. So I appreciate all your questions. It's been a good session. I have small amounts of travel in the next week or so, but basically we'll get back on our routine of every week or so for the live sessions, and I look forward to the next one. Thank you.